So firstly, I wanted to confirm whether you received this write-up. Professor Das actually wrote it up so that there's a formal proof for you to read. Last time that we saw epsilon NFAs with epsilon transitions, we had a brief discussion, and then I had asked you to formally prove it. So what we were discussing is regarding construction of an NFA where the epsilon transitions can be left out. But as you also know that you can also construct a DFA. If you can construct an NFA, you can also construct a DFA. And there is a formal proof for showing how this DFA construction can be done. So what we had discussed earlier was that you can, if there is a path that is completely labeled by epsilon, then you should also be able to take that path and see where you reach. That was the point of epsilon transitions. So now, briefly, you can define your delta hat transition, multi-step transitions in such a way that you include all those states that you reach where you have traveled. So if you consider the labels of the path, that path starting from some t and ending in this set delta hat t epsilon, then this path will be labeled by, so basically the string x will be a subsequence and the rest of the alphabets will be epsilons. So some of the portions will have epsilon paths and then you continue with reading x. So there's a formal way of writing this down, and then once you have this, you can construct a DFA using subset construction. So please go through this. Uh, if you haven't received this email, I have sent it via ERP. So if you haven't received this email, please send me an email or write down in the post section of the team, because it's a very good write-up. You also have examples. I think it will help you to understand the epsilon transitions. Okay, so let's continue with our discussions on finite automata and on. So finite automata gave us we saw that languages that are accepted by finite automata, be it DFAs or NFAs or even NFAs with epsilon transition, they were all accepting regular sets. So non-determinism or non-determinism with epsilon transitions did not add power to the mathematical model of finite automata. All of them were equivalent. All of them could accept only regular sets, not more than that. So now we are also going to be looking at another form of mathematical finite representation, that is pattern matching. So this is I mean, there is a practical application for this. If you consider, when we type, let's say star dot some extensions, let's star dot PDF, and you suppose you type ls star dot PDF on your console, and then you get the list of list of files that have PDF extension. So this is a sort of pattern matching that you're doing. You're saying that, okay, any name before that does not matter. I'm representing that with star. So any such name is going to map to star. And then this dot PDF is all I want to be mapped one to one. So these are of practical usage. You can represent. So for example, if you consider your set of files, a set of PDF files, you are representing in your computer, you're representing each of these files with a name. Let's say some a.pdf, b.pdf, and so on. And then this entire set you can represent by star.pdf. So your computer is reading this as this entire set as a much shorter string. You're representing all this entire set by a much shorter string. So suppose you had a.pdf, b.pdf, and so on. Let's say z.pdf. And this could be represented in a much shorter way as star.pdf. Let's say we are in a particular folder. So your computer is doing this sort of pattern matching where all these A, B, and so on. These are getting compressed to this particular star. All of them are going to be mapped to star, and it's just this dot PDF that is being mapped one to one. So now the question is, can we do the same thing for other languages? And this pattern matching is interesting because not only is it an important application for the computer, but when you the actual mechanism for implementing this application is finite automata. So when you run these programs grep, fgrep, or egrep, then so these are pattern matching commands, and they actually use finite automata to implement to be implemented. So this is very interesting. But so far we don't know whether the two things are the same or not, whether pattern matching and finite automata are the same or not. For now, we can think of these two as two kinds of mathematical finite representation of languages, where finite automata we've seen are mathematical modelings of languages which are regular sets. Now let's see what happens for pattern matching. So suppose again we take sigma to be the set of input finite symbols. A pattern is a single string of symbols. Maybe you are adding some more symbols which are outside sigma. It's a single string of symbols that represents a subset of strings in sigma star. So as an example from what we saw earlier, if we had a.pdf, b.pdf and so on, we were representing the entire set by a single string, but maybe you are using some symbols which is outside sigma star. Now let's come to the mathematical definitions of how we can look at a pattern. So we will be considering two kinds of patterns, atomic and compound. From the names themselves, you can sort of understand that a pattern is going to be defined in an inductive fashion. So let's get into this. Just for notational convention, we are going to be using Greek alphabets like alpha, beta for patterns. The atomic patterns are of 5 kinds. So suppose we are considering the set sigma for now of input symbols. Then for each symbol in sigma, we will have an atomic pattern corresponding to it. So for every A in sigma, we have an atomic pattern corresponding to it. Then we have an atomic pattern epsilon, an atomic pattern null, atomic pattern hash, and atomic pattern at. So now let's see what is the set of strings that is being represented by each of these atomic patterns. Suppose you're given a pattern alpha, then I will denote by L alpha all the strings X such that X matches the pattern alpha. So by using this notation, let's see what are the strings, the set of strings that match to each of these atomic patterns. Notice that if I just have a single symbol from the set of input symbols, then only that symbol is going to match to that single symbol. There can be nothing else. Consider the atomic pattern epsilon. Only the empty string is going to match to epsilon. What about null? The null set is going to match to null. Hash, the set of input symbols is going to match to hash. Meaning L of hash is equal to A1, A2, AN, where A1, A2, AN is equal to sigma. And what about at? All strings in sigma star all strings will match to at. So this is the basic idea of atomic patterns. You have a atomic pattern for each of the symbols of the input set of symbols. You have a symbol for your empty string. You have a symbol for your null set. You have a symbol that represents each of the singleton strings that can be constructed by from sigma. Each of the singleton strings that are from sigma. And you also have the pattern at, where no matter which string you give, it is going to match to at. Okay, any questions for atomic patterns?
Ma'am,
Yes.
A for each A belonging to sigma means for a single symbol we are matching it to itself.
To itself, yes.
Okay, okay, ma'am.
Yeah. And hash is where you are matching each of the singleton symbols to hash. So L of A is going to be A, meaning L of A1 is going to be A1 and so on. And L of hash is going to be each of these singleton symbols. Okay?
Okay, ma'am.
Okay. So these are the atomic patterns, and these are the languages that are matching to each of the patterns. Now we want to inductively build up two larger patterns, and these will be called compound patterns. So the inductive definition will be using binary operators and unary operators. In binary operators, we will be using union, intersection, and concatenation operations. For unary, we will be using the star, the unary plus, and the not operators. And this is how we will be compounding the patterns. So suppose you have two patterns alpha and beta. Suppose you have alpha and beta, then you can use these binary operators and the unary operators to form the compounded patterns alpha plus beta, alpha intersection beta, alpha concatenated with beta, alpha star, alpha plus, and not of alpha, which sometimes will also be denoted as follows. Okay, so now we have constructed the compound patterns, but what is the language matching to that pattern? So this should be fairly simple. A of A plus beta, L of A plus alpha plus beta is going to be equal to L of alpha union L of beta. L of alpha intersection beta is going to be L of alpha intersection L of beta. L of alpha concatenated with beta will be L of alpha concatenated with L of beta. Then L of alpha star is going to be L of alpha whole star. So notice that even epsilon, L of alpha star should contain epsilon, and L of alpha whole star is also containing epsilon. This is one basic check. L of alpha plus, this will be L of alpha whole plus. So this is concatenation of length of strings which are of length at least 1. And finally, L of not of alpha is going to be not of L of alpha, which basically means you take sigma star and you leave out all those strings which are matching to alpha, which means you leave out all those strings in L of alpha. Okay, any questions regarding compound patterns and their languages? So far, fairly simple,
Ma'am,
obvious definitions. Yes?
ma'am,
Ma'am,
how L of alpha star is equal to L of alpha whole star? Like, alpha star may contain this epsilon, but L of alpha star may not contain epsilon.
No.
no.
So you're saying on the left hand side there, it will not contain epsilon.
No,
You're
ma'am,
saying
it will
L of,
contain epsilon.
huh?
It will
The
contain
right
epsilon.
hand side definitely contains epsilon, right? Because you're taking A star will always contain epsilon.
Okay, ma'am, sorry.
Yeah, yeah. Okay.
Ma'am,
This
Yes.
alpha, beta, these are all strings, right?
Alpha, beta are strings, but not strings from sigma star. These are strings the way we have defined patterns.
Uh,
So,
yes, ma'am.
yeah,
With some additional alphabets
there will be
outside.
some, yes.
But what is the meaning of intersection of two strings?
This is how we are defining the intersection. That look at L of, so for every pattern, so you can think of alpha as a pattern and beta as a pattern. For every pattern, L of alpha will exist and L of beta will exist. These are this is the language matching to alpha. This is the language matching to beta. Now we are saying when I denote alpha intersection beta, this is a pattern that requires uh, all those strings to match to this particular pattern, all those strings that are matching to this particular pattern denoted by L of alpha beta should be the ones which are matching to alpha as well as beta.
Okay, ma'am. So we are defining the operations here.
Yes, yes. So far it's just definitions. Even before that, atomic patterns and their languages, these are just definitions. Similarly,
Yes, ma'am.
compound patterns and their languages, these are the languages matching to them, these are definitions.
Ma'am,
Ma'am?
but what about like how can we guarantee that alpha intersection beta is an unique pattern?
What do you mean by unique pattern?
I mean, there can be multiple strings that have the same L of, like they match to the same
Yes.
subset.
Yes, that's true. We haven't like this is not unique. We
Okay.
haven't discarded the fact that two patterns can have the same language matching to that. That's a very good question. So it is possible that two patterns match to the same language. The same language matches to two different patterns.
Okay, ma'am. Okay, ma'am.
Yeah. Okay. Somebody else had a question?
Ma'am, can you please explain the third definition once again?
This one?
Yes, ma'am.
Yeah. So when I say alpha concatenated with beta, so this pattern, the pattern alpha concat beta, then what I want from the language match to alpha concatenated with beta is look at all strings matched to alpha. That is the first language. Let's call it A. Look at all strings matched to beta. Let's call it B. I want the language A concatenated with B to be all strings in A concatenated with B to be matched to alpha concatenated with beta.
Okay, ma'am. Got it. Thank you.
Ma'am,
And now you just continue this concatenation definition. You continue over here for the next 2 points as well.
ma'am, but when we are concatenating alpha and beta,
Hmm.
so they are continuous in L alpha dot beta. But on the right hand side, the strings matching to L alpha and the strings matching to L beta.
Yeah.
So in between there can be some more like some more tag words or like letters.
Like what?
Let's say like we are matching IIT Kharagpur. So
Hmm.
so alpha is let's say double I and beta is GP.
Hmm. So then this does not match to L of alpha concat beta, right? Where are you getting this? Sorry. Where are you getting this? That's
Yeah,
not
yes,
possible.
ma'am. But right hand side it matches, right?
Why?
Ma'am,
How will
IIT
it match?
matches to L alpha and GP matches to L
No,
beta.
no. How does IIT match to L alpha?
Okay, are we like exact matching?
Yes, yes, yes. So
Okay, okay.
if you consider the atomic patterns, this is exactly how they are matching, right? I'm not. So if I want to, if I okay, maybe you're confusing with the start.pdf example. That the star could be anything, but even in the star.pdf example, it's the star that is matching to whatever a.pdf, b.pdf, and then the dot pdf is matching to dot pdf. So there is some sort of mapping. You cannot add anything in between.
Okay,
It's
ma'am, yeah.
like a b. Suppose I had a.pdf, b.pdf. Then it's like A is matching to star, B is matching to star, and then this dot PDF is matching to itself.
Yes, ma'am.
And similarly, instead of star dot PDF, if I had said A star dot PDF, as you may have checked, A star dot PDF, then this will not match. B dot PDF will not match. Okay?
Yes, ma'am.
Okay. Okay, so far definitions of patterns. So basically we are trying to capture languages by a single string. Maybe we are adding some more alphabets to represent that string. And we defined in an inductive manner how to construct patterns and what we mean by the language matching to that particular pattern. So now we should be looking into what are the kinds of languages that match to patterns. So before that, let's look at some properties of matching. So basically we saw that patterns are strings over symbols sigma dagger, where it is a superset of sigma, where the extra symbols are epsilon, empty, hash, at, binary plus, intersection, concatenation, unary plus, unary star, not, and then you also have some brackets. Also notice that in order to define the language matching to hash, at, and not, you need to know what this sigma is. For everything else, it is more or less independent of sigma, but for these particular things, you need to know all of sigma. Now let's look at just to have a better understanding, let's look at a few examples of what I mean by what are the languages that are matching to given patterns. So suppose X in sigma star is a pattern. I'm just taking X as a pattern. That is allowed because patterns are strings over symbol sigma dagger. Now, now you just restrict yourself to sigma itself, and you write any X which is x1, x2, let's say till xn. Then notice that the language that is matching to this particular X is X itself. Nothing else can match to it. Now, what about L of x1 plus x2 plus x3? x1, x2, x3 all comes from sigma star. What will this language be? Somebody, what will this language be?
x1, x2, x3.
Right, x1, x2, x3. What are the languages? If you consider x1, what will this be? This is by definition L of x1 union L of x2 union L of x3 by definition. And now from before we know that L of x1 is x1 itself. Then L of x2 is x2 itself, and L of x3 is x3 itself. And therefore this will basically be x1, x2, x3. Okay? Okay, so there's another thing that since we are considering an expression like this, plus is associative. So even if you took x1 plus x2 plus x3, this pattern will be equivalent to x1 plus x2 plus x3. So the two language, what do I mean by equivalence? The two languages will be the same. Similarly, if I consider the concatenation operation, if I took x1
That means the languages matching to these two patterns are the same.
Yes, the languages matching to x1 to the, let's call this alpha and let's call this beta, then L of alpha is equal to L of beta. That's when I will say alpha is equivalent to beta.
And then is it a like, shouldn't languages uniquely be identified, like patterns uniquely be identified by the languages that match to them? Like
You're saying if I have a particular pattern, one direction is correct. If I have a particular pattern alpha, then there is exactly one language matching to it. But if I give you a
yes,
language L, L could be equal to
yes,
L
ma'am,
could
that
be
is
equal,
obvious.
L could be this. This is possible.
Okay, ma'am. Yes, I got it.
Because just look at this particular example. These are two different patterns. You can think of them as two different patterns because they are two different strings. If you consider sigma dagger, then where you put the brackets gives you a different string. So this, the left hand side is a different string in terms of sigma dagger star. This is a different string from the right hand side string. But they are both if you consider the languages from definition, they will both give you the same language.
Yes, ma'am. Okay.
But this is a trivial example. It could actually, you could, we will later on see patterns, simplification of patterns, so that you represent the same language, but you decipher a better structure in the patterns. We will look at this later.
Like the singleton set X matches to X and also X union Y or something like X plus Y or something like that.
Why?
No, means I'm saying that one language can match to multiple patterns, but one pattern will have only one language.
One pattern will have one language, that is correct. But again, so what you said is not completely correct. Singleton pattern, the example you gave is just saying this is a subset of L of X plus Y. I think what you can give is, let's see. If you wrote something like this, then this would be equal to L of X. Okay?
Okay, ma'am.
Ma'am,
Yes?
ma'am, what is like plus operated over two patterns? Like what does that operation do?
Just the union. So as we saw earlier, plus operation, plus is just, we are just constructing a pattern. Right now it does not mean anything. If I just say alpha plus beta, it does not mean anything. The only time we are giving meaning to it is by considering languages, because we are only interested in the patterns because we want to consider what languages matter to that particular pattern. And alpha plus beta is going to be denoted as a pattern that matches that pattern that matches to the set of strings that belong to L of alpha as well, L of alpha or L of beta. This is just a
Understood,
way
ma'am.
of representing.
Understood.
Yeah. Similarly, L alpha intersection beta. A priori does not mean anything. What is the meaning of intersection of two strings? But basically, we are giving meaning to it by associating particular languages to these particular patterns.
Okay, ma'am.
We have a particular, probably you're confused with this star.pdf example. Star.pdf is an application. Like grep or all these pattern matchings for file searches, that is an application of pattern matching. So then now we are into the mathematical modeling of that. In the mathematical modeling, we are trying to find finite strings that can represent a particular language. Just like we were doing for finite automata, that was also a mathematical way of finitely representing a language that could be that could have infinite strings. Again, pattern matching is another way in which we are constructing strings. Maybe they have some extra symbols, some symbols more than sigma itself, but we are constructing a string that represents a particular language. And this representation is what we are calling matching to a particular pattern. If we are representing a language with a pattern, then our objective is to say that every string in that language should be matching to this particular pattern. And for that, we have developed we are developing a way or a mathematical inductive way of writing. That is, if I have alpha plus beta, I want to represent that language which has all strings matching to alpha or matching to beta. Similarly, intersection and so on. We are developing a mathematical language to find a mathematical finite representation of a set of strings.
Ma'am, here alpha plus beta is a string, or is it like two operands being operated upon by the plus operator?
Yeah, so two strings operated by the plus operator does not mean much, right? You have this plus intersection operations on sets of strings. These are not to be operated on strings. So just like that, alpha plus beta does not mean anything. It's only when you associate these languages that alpha plus beta as a pattern means something. When you learned binary operations, it wasn't on strings, right? It was on sets of strings. Or even the unary operations, these are on sets of strings. These are on sets of strings, not on strings themselves. So just like that, these things don't mean anything. They only mean something when you're associating sets with them. Fine?
Okay, ma'am.
Any other questions?
So, ma'am, whenever we are trying to match a string to a pattern, we are just checking that whether that string belongs to the language recognized by that pattern. So that is the
Correct.
problem we are solving.
Correct,
Okay.
correct, correct.
Ma'am, that doesn't mean that it may not be necessary that that particular string that we are checking, that pattern is not found in that string. Like in IIT KGP.
Okay, let's take IIT KGP.
Like this is a particular string, and can it happen like that the pattern that we are choosing is I, just like the previous person said.
Okay, so first one, let's say I. Then?
So like can we define some other pattern for this whose substring is not found within this? Like
yeah, I can think of, so I can think of patterns where this, let's take this particular string S as example. Let me take alpha to be II and let's take it to be TKGP, and then you know that S is going to belong to the language of alpha concat beta. Now let me take alpha 1. Let's call this IITKGP. Let's call beta something else, M. Notice that S also belongs to the language alpha union beta because it matches to, alpha 1 union beta 1.
Yes, ma'am. Because it belongs to L of alpha 1.
Right. So, but you cannot, I mean, just from the definition of patterns, just how we defined it, you cannot match. So the last example was taken as alpha is II and beta, let's say GP. Then just with these binary operations or from the atomic patterns, you cannot match S to, let's say if I take, let's take alpha and beta. We have these particular ways of defining patterns, right? So using just alpha and beta, if I take alpha plus beta, we saw what alpha plus, this will be plus. We saw what alpha plus beta can be. We have definitions for what alpha plus beta is. This will be just L of alpha union L of beta. IIT KGP does not belong to L of alpha. IIT KGP neither belongs to L of beta, right?
Yes, ma'am.
So it is possible. Maybe you can get some. I mean, right now, I don't think IIT KGP will be one such thing. But suppose you had III, GP. Then you can construct something just from alpha and beta. It will be some L of alpha square, beta square, let's say, or L of alpha star, beta star. It's possible. You can have the pattern that you're matching can be quite complicated, and there may be more than one patterns to which you're there may be more than one patterns to which this particular string can match. For example, this can match to multiple patterns, meaning that this string belongs to different languages that are matching to combinations of alpha and beta. And it's also possible, not for this particular example, it's also possible that these two patterns represent the same language. All these things are possible. But giving out a gap like this is not possible. Just from the definitions of the patterns that we have given so far, from the atomic patterns and how we are building up to compound patterns, you will not be able to construct, you will not be able to produce this T and K symbol just from alpha and beta, where you don't have T and K appearing anywhere. There must be something else that you're doing in order to get this T and K to match.
Okay, ma'am, got it.
So it is
Thank you.
possible that you do alpha hash star beta or something. If you add something more, then sure, you may be able to match it. I hope this point is clear.
Yeah, ma'am. Thank you.
Okay.
Ma'am,
Yes.
ma'am, alpha plus beta means concatenation, right?
Alpha plus beta, no, union. Alpha dot beta means concatenation.
So, ma'am, what does alpha plus beta means?
Alpha plus beta is this. Alpha plus beta is, look at the strings that are matching to alpha plus beta. They must either match to alpha or match to beta.
Okay, sir. Okay, ma'am.
And alpha concat beta is all the strings that match, that can be broken into two parts. So these two, I mean, this is a good point that you're pointing out. The first thing, alpha plus beta. So alpha concat with beta is a little bit more structural for the strings that are being matched. So alpha concat with beta is all strings, let's call them Z, such that Z can be broken into two parts: X concat with Y, X matching to alpha and Y matching to beta. Here, in alpha plus beta, all strings matching to alpha plus beta basically only match to either match to alpha or match to beta. They could match to both. So this is a little bit more structural for the strings that are matching to alpha concatenated with beta. Okay.
Yes, ma'am.
Okay, any more questions? Yeah, so we were at the point where plus is associative and so is concatenation. So meaning if I have x1 concatenated with x2 and concatenated with x3, this is a string in over sigma dagger, and so is x1 concatenated with x2 concatenated with x3. Because of the positioning of the brackets, these are two separate strings in sigma dagger, but L of this is equal to L of this. Okay, so let me move forward. Now let's look at another example at A. So remember that, so these are concatenation signs, right? So what will L of at A be? This will be L of at concatenated with L of A, concatenated with L of at, concatenated with L of A. So notice that L of A is just going to be A. This is an atomic pattern which matches to itself. So L of A is just going to be A. L of at matches to sigma star. Similarly, L of at matches to sigma star. So it could be any string from sigma star followed by A, followed by any string from sigma star followed by A, which basically means the set of strings which have at least two A's and which also ends with A. This is what this pattern means. This pattern represents this set of strings with at least two A's and ending in A. Let's look at another example. I want to construct a pattern for a language over sigma. Sigma is the base symbol. So sigma dagger will be built over sigma. I want to build a language where every A has at least one B after it, meaning that it is possible. So AAB may also be contained in this language. The same B could be after two A's. It doesn't have to be unique. So the question is there a pattern alpha such that L is equal to L of alpha? And this is one way of representing this language. So what does this say? The first part is hash intersection not of A whole star. This means I am taking sigma minus A whole star. The language represented by the first part is sigma minus A whole star, meaning you consider all those strings which does not have an A at all. Those strings should belong to the language L just by definition, this condition is trivially satisfied. Every A has at least one B is trivially satisfied. So sigma, any string in sigma minus A whole star will be in this language L. Next is, now what are the strings that are left? The ones which contain A, but now we have to ensure that after every A there is a B, which means, which can also be rephrased as after B, after the last B, after last B, no A appears. And this will be represented by this. So I take any sigma, I take any string from sigma star, let's call it A, and then let's say B appears at some point. After that, there should be a portion which is clean of A's. There could be more B's, but there should be a portion that does not have any A's, and that is represented again by hash intersection not A whole star. So hash intersection not A, this will represent sigma minus A, right? And this is what we are using here as well as here. And hash A intersection not A whole star will be all those strings that do not contain A.
Ma'am?
Any question? Yes.
Ma'am, sigma minus A whole star. Ma'am, why have you written this in the very first argument? I mean, why is there is a need of that?
Because these strings have to be represented, right?
Ma'am, I want to say that in the very beginning you have written sigma minus A whole star, which means all those strings where A is absent.
Right.
So ma'am, according to question, ma'am, why you have written that?
Because in the question, look at the set of strings in L. You can divide L into L1 and L2. So this L2 contains A and L1 does not contain A. Right? If L1 does not contain A, then trivially this is satisfied, right?
Yes,
no,
ma'am.
not this one. Sorry, not this one. Trivially this is satisfied. Every A has at least one B. So L1 will also belong to L. But look at L2. If there is a string that contains at least A, then I must ensure some more structure. Then let's look at this string X. It can be broken into X dash followed by B and then a Y, where Y belongs to L1. Y does not contain any A. Correct or not?
Ma'am, after the very last B, there should not be any A, right? So ma'am, isn't it this is the only condition that we need to satisfy?
No, because it is possible that a string does not contain any B. Here
Okay,
we
yes,
are
ma'am.
ensuring that a B must be there.
Yes, ma'am.
Yeah. Okay.
Yes, ma'am.
Ma'am,
Understood.
ma'am, we can write this hash intersection not away as epsilon minus A also. I mean sigma minus A also. Means notationally we can write these
This
two.
one? This?
Yes, ma'am.
You can't, right? Because this is sigma is not part of the symbols you can use in a pattern. This is a pattern. Notice that this is a pattern. All the symbols come from sigma dagger. What I can say is L of hash intersection not A star. This is equal to sigma minus A whole star. But I cannot write it as sigma minus A. That's
Okay,
just, by definition, that's not possible. What you're saying is correct, but by definition, it won't be a pattern. The languages are the same.
Yes, ma'am. It's the language, not the pattern.
Yes, yes. The languages will be the same, but the pattern, it can't be written in the pattern.
Yes,
And when
Ma'am,
the
what will happen? Ma'am, what will happen if there are no A's and no B's?
Can you tell me in which category it will already be covered? I'm saying the first part corresponds to L1, second part corresponds to L2. If there are no A's and no B's, will it be covered by one of the two parts?
L1.
Right. That will be contained in L1, right?
Yes, ma'am.
One more person had a question.
and the languages matching to both these L1 and L2, these patterns, they are not necessarily disjoint, right?
Not
They are just
necessarily, yeah.
their
Not
union is just
necessarily.
giving us what we want. Like
Sorry?
their union is just giving us what we want.
Correct,
Like
correct. L1 and L2 need not be disjoint because
yes,
consider all those strings in L1 that contain at least one B.
yes, ma'am.
That could appear in L2 again.
Yes, ma'am.
But that's the point of unions, right? You don't care about whether there is an intersection or not.
Yes, ma'am.
Anything more? So one question that somebody asked and I want to point out is this is a pattern and L is the language that is matching to this pattern. So there are specific things that we can write in a string that is representing a pattern. We cannot write sigma, we cannot write certain things. A pattern has to be built over symbols from sigma dagger. But the pattern only makes sense when you consider the languages that are matching to that pattern. And the language matching to this first part is sigma minus A star. But this cannot be directly written into a pattern. Okay, can I move forward or are there more questions?
Ma'am, instead of writing at the rate, can we write sigma star?
No, you can't, right? How will you write it? You don't have that in sigma dagger. At least in the pattern, you can't.
Okay, ma'am.
Yeah, okay. Okay, and just to see whether our understanding is fine, suppose the above language L was over sigma being A comma B, then the point is that the pattern will be much simpler because it is possible that there is no it is possible that you have an epsilon string, otherwise any other string sorry, once more. It is possible that you have the empty string as part of the language. Otherwise, it's not even the empty string will be part of the language. Otherwise, it must be true that at least one B is there. All A's will not be accepted will not be in this language. At least one B is there. And therefore, if at least one B is there, all you need is that the last alphabet is B. Then notice that you will have covered all the cases where any A is followed by a B. So this is when sigma becomes A comma B, then the pattern becomes much simpler. So the argument again is epsilon, the empty string belongs to this language L. If you again think of L1 and L2, L1 not containing any A, and L2 containing some A. So epsilon belongs to L1. Okay, so we write epsilon separately. The atomic pattern epsilon separately. Now let's consider anything else in L1. Anything else in L1, if it does not contain A, it just belongs to B star. Now let's consider L2. Anything that contains A and has to satisfy this particular property must have the following structure, that the last symbol is B. You cannot have an A afterwards. So it will be some X B where X belongs to A comma B star. Right? So epsilon is covered by this and the leftover from L1 and L2 is covered by at B. Because A or B can match to any string. Any string in A comma B star can match to at, but the criteria is that at the end you must have a B. You cannot have an A. Fine?
Excuse me, ma'am.
Yes.
Do we obtain the same reduction on putting hash as A and B? Like, why are we getting that from this?
I did not understand your question.
Ma'am, like in the previous we had a general result. So are we getting this reduction from that general result?
Not really, because we are, as we saw, we have two kinds of sets. In the previous one, this was or L1 was being matched to this, and L2 was being matched to this. But here, L1 is again being broken into two parts. We are looking at L1 and we are seeing that it is basically epsilon union B star. Let me write it properly. L1 is basically epsilon union X belonging to B star, right? So let's call this L1 dash. And L2 is anything that contains some A, but in order to satisfy the property of the language, it must be true that it is of the form XB, where X comes from AB star. So now epsilon, this is being represented by epsilon, and this is representing L1 dash union L2. So this is not really a direct, epsilon is not L1. Epsilon does not match to L1. L1 can have more things, but they match to at B. Fine?
Yes, ma'am.
Yes, someone else has a question.
Yes, sir.
Yes.
For example, in L2, if we have x is equal to AA.
Suppose AA belongs to L2.
No, ma'am, the string x.
Oh, okay. Yeah, okay.
Ma'am, this AAB doesn't follow the language because.
Yes. It does not have to be. Two A's can have the same B following it. It doesn't have to be unique to a particular A.
No, ma'am, the condition is every A has at least one B, but the first A doesn't have any B after it.
So it is going to, this B is going to be considered to be after this A as well as this A.
Okay.
Yeah. Any other questions?
Ma'am?
Yes.
Ma'am, here B star plus @ B would also be a correct pattern, right?
Okay, let's see. This is plus, you're saying B star plus.
No, ma'am. Instead of the first epsilon, if I write only B star.
Oh, okay, sure. Good. This is also a pattern.
Okay, but then
at the rate B star.
What do you mean at the rate B star?
No, then
at the rate B star.
No, not at the rate B star, right? Because that would mean you have A star. A star will belong to that language. At the rate B star is not possible.
Okay, ma'am.
B star plus at B is fine. At the rate B star would mean that you may have a string ending in A.
Yes, ma'am. Got it.
But B star plus at the rate B, this is correct. This is also a pattern representing this particular language over AB. You consider, look at L1. L1 is going to be L of B star and L2 is going to be at B. Actually, L2 will have some more things. It may not contain, at B may not contain A. We are not demanding that it contains A. This second part will have L2 plus something more. But you can represent L1 as B star. Okay, so good. So we have two representations, two patterns that match to the same language. Okay. So I'll just, yes.
Ma'am, I'm not able to understand the meaning of at the rate.
At the rate is just representing, if I write this symbol at the rate, the language associated with at the rate is just going to be sigma star. At the rate is an atomic pattern. The language associated with at the rate is sigma star. So basically I'm saying wherever I see at the rate, in place of that at the rate, I can put in any string from sigma star. So suppose I saw, let's say I have L at the rate union X, let's say. That, what does this mean? Can you tell me from definition, what would this mean? What would this language be? Whoever asked the question, what would this language be?
Sigma star
Sigma star union
L of X.
What is L of X?
Language accepted over string X.
X is something from sigma star. So what will L of X be?
I'm not getting, ma'am.
What will, so X is in sigma star. X can also be a pattern.
Yes, ma'am.
L of X is X itself, right?
Yes, ma'am. Okay.
So then what is sigma star union X? What is sigma star union X?
Sigma star only.
Sigma star itself, right? X is a string of sigma star.
Yes, ma'am.
So L of at the rate union X is a string from sigma star, not, it only contains symbols from sigma. Then L of at the rate union X is just going to be sigma star itself. Now suppose I said L of at the rate dot hash. What would this string be? What would this language be?
Ma'am, sigma star plus L of hash.
Plus?
No,
This is
no,
concatenation.
intersection.
No. This is concatenation, not.
Okay.
Concatenation L of hash. So basically this, please see, this will be sigma plus. You will just not have epsilon. Everything else will be there.
Okay, ma'am.
Got it?
Ma'am?
Yes.
Ma'am, you said at the rate B star would also have some strings ending at A. Ma'am, can you show that how is this is coming?
So L of at the rate B star is equal to L of at the rate concatenated with L of B star. And now L of at the rate contains, let's say some A.
Yes,
A.
ma'am.
And then L of B star contains an epsilon.
Epsilon. Yes, ma'am.
Yeah.
Yes, ma'am. Got it. Thank you, ma'am.
Okay. Any more questions?
Ma'am,
Yes.
isn't L1 a subset of L2?
L1 subset of L2. Yeah, I think it will be. I mean, except for epsilon, if L1 dash is a subset, no, not of L2. No, not of L2, right?
L2 is also containing patterns without A, na, ma'am?
Once more, L2 is contained in?
Containing patterns without A.
No. L1 and L2 I have defined as L1. Look at L. I have broken L into two parts, disjoint parts. L1 containing A and L2 containing anything. L1 not containing A and L2 containing A. Now, okay, maybe you got confused with this. I think. So this XB, all patterns XB, L2 will be contained inside these kinds of strings. The set of strings L2 will be a subset of all sets of the pattern XB, where X comes from AB star. L2 will not have X coming from AB star, because it is possible that X only belongs to B star. But I don't need to force where A is going to appear, because the rest of the things belong to L1 dash.
Okay.
Okay, so one more thing. Was your question about this? Because even this is not exactly L2 itself. You may have some strings from L1, but L2 matches to this string. Some strings from L1 can also match to this string. This pattern, sorry, this pattern. So the second term, I think this is what you were trying to point out. The second term in both the expressions are not exclusively matching to L2. I mean, L2 is not exclusively matching to the second terms. There may be some strings from L1 where B occurs but A does not occur. Those may also match to the second terms as well. I think, was that your point?
Yes, ma'am.
Okay. Okay, so I'll just leave with a few questions and then we'll continue tomorrow. The first thing, so these are some natural questions that will arise. First is, how do we exactly check whether a string matches to a given pattern or not? We don't really know. So far, we've just seen definitions. How do we actually check whether if I give you a string, does it match to a pattern? Next question is, if I give you a set of strings, can you give me a pattern that matches to this particular set of strings? Now, one point that I want to make out is that a pattern is a string over sigma dagger. So again, the number of such patterns are countably infinite. So again, that same point comes back. The number of such patterns is countably infinite, but the number of possible subsets of languages is uncountable, and therefore it is possible that there are sets that cannot be matched to a particular pattern. But the question is, you can formulate it as, if I give you a particular set of strings, can you give me a pattern matching it? We know that from this countable, countably infinite and uncountable argument, we know that there will exist some languages which will not have patterns matching to that particular language, and we will see explicit examples as well. In a few classes, you will also see explicit examples. But given a set of strings or given a language, can I design a pattern for it? That particular language, I mean, if I give you a specific language, for example, this particular language, if I gave you this particular language, you were able to design a pattern. So is this possible? Look at the problem where you're given a specific language. Can you design is there a mechanism for designing a pattern for that? Second, the third question is what one of you have already asked. Two patterns will be called equivalent if their languages are the same. So how can we find out whether two patterns are equivalent or not? And the fourth and last question is, which operators are redundant? Because see, if I have the not operator and if I have the and if I have the or operator, then using since these are operations over sets, basically the languages matching to pattern alpha union language matching to pattern beta and so on. You can, using De Morgan's laws, you can represent the AND operator, the intersection operator. So can we say that some operators are actually redundant and reduce my sigma daggered set? So these are the four questions that we will be addressing in the next class on tomorrow. And actually what we will see, I think you are getting a hint of it, what we will see is that all languages that are accepted by, that have patterns, that match to patterns, are actually regular sets. So patterns are also another way of representing regular sets. Okay, so any questions regarding today's class? Okay, then I'll end the class and we'll meet tomorrow. Thank you.
Thank you, ma'am.
Ma'am, please stop recording.
Thank you, ma'am.
Thank you, ma'am.